Learn like a pro.
All right, let's stage the ultimate chemical showdown. In one corner, you've got the flashy, super reactive alkali metals of Group 1, and in the other corner, the colorful, intense halogens of Group 17. Trust me, this is not your average, boring chemistry lesson. This is a head-to-head battle for one thing: stability.
And you know what? This whole rivalry, it really just boils down to one simple question. See, one group gives, and the other group takes. But why? It's kind of wild when you think about it. Their entire chemical personality, everything they do, it all comes back to this one fundamental difference.
Okay, so let's get into it. Let's break down the rules of the game here. It all starts with the most important contest in all of chemistry, what I like to call the electron game. The rules? Super simple. The stakes? Well, they're everything.
So let's meet our competitors. First up, we've got Group 1, the alkali metals. We're going to call them the givers. Why? Because they have just one single valence electron. That's the electron in their outermost shell, and they are absolutely desperate to get rid of it. Then you have Group 17, the halogens. We'll call them the takers. They are just one electron short of being perfect, and believe me, they will do pretty much anything to get it.
So, what's the prize? What are they even fighting for? Well, they both want to be like the cool kids on the block. Group 18, the noble gases. I mean, these elements are the definition of stable. They've got a full outer shell of electrons, which basically means they don't need to react with anyone. They are totally, completely satisfied, just chilling. And you better believe Groups 1 and 17 are super jealous.
So, what's Group 1's strategy to win this game? It's simple, actually. They just give up. See, they start with this one lonely electron in their outer shell. By just donating that one electron, poof, they expose a full, stable shell underneath. They become a positive ion, and they get that sweet, sweet noble gas status. It's like addition by subtraction.
Now, Group 17, they've got the exact opposite strategy. They start with 7 valence electrons. I mean, they are so close to a full set of 8. So their game plan is to just aggressively snatch one more electron from some poor, unsuspecting atom. Once they do that, they become a stable negative ion, and bam, they've finally completed their outer shell.
Okay, so we get their motivation now, right? It's all about the electrons. But how does that affect what they actually look and feel like? Let's dive into round 2, the physical properties showdown. And wow, when it comes to physical properties, they could not be more different. The Group 1 elements, they're your classic metals. I'm talking so soft you can literally cut them with a knife. They're shiny, and they are fantastic conductors of heat and electricity. And Group 17? Total nonmetals. In their solid form, they're brittle, they come in this whole range of amazing vivid colors, and they are awful conductors. They are complete and total opposites. Let's zoom in on the halogens for a second, because they're pretty fascinating. As you go down the group, you see this really clear, colorful pattern. You start with fluorine, which is a pale yellow gas, then chlorine, a yellow-green gas, then you get to bromine, this cool reddish-brown liquid. It's actually one of only 2 elements that are liquid at room temperature. And finally, you have iodine, a striking purple-black solid. I mean, you can see that beautiful progression right there. It goes from gas to liquid to solid. So what's actually going on? Well, as you move down Group 17, the elements just get heavier. This means the attraction between their molecules gets stronger, and that's what changes their state. Pretty neat, right? Okay, now here's where things get really interesting. Let's compare their trends. As you go down both groups, their density increases. I mean, that makes sense, right? The atoms are getting bigger and heavier. But look at the melting point. For the Group 1 metals, it actually gets easier to melt them as you go down the group. But for the Group 17 halogens, it gets harder. What's up with that?
All right, it is time for the main event. This is the round that decides it all. Reactivity. Just how badly do these elements want to win that electron game? Let's find out. Okay, this is probably the most crucial point to remember. The trends here are perfect mirror images of each other. For Group 1, their reactivity increases as you go down the group. It gets easier and easier for them to give away that outer electron. But for Group 17, it's the opposite. Their reactivity decreases as you go down. It gets harder and harder for them to attract a new electron.
So why? Why these opposite trends? It all comes down to something called electron shielding. Think of it like this. As the atoms get bigger and you go down a group, that outermost electron gets farther and farther away from the positive nucleus that's trying to hold on to it. And not only that, but all the inner shells of electrons act like a shield, blocking the nucleus's pull. So for group 1, this makes that outer electron super easy to just let go of. For group 17, that same shielding makes it much harder for the nucleus to reach out and grab a new electron from somewhere else.
And when I say group 1 is reactive, I am not kidding. These metals are so desperate to give away that electron, they will react violently with just the moisture in the air. That's why you have to store them under oil, to literally keep them from touching water or air and, well, exploding.
So what happens when these rivals finally meet? Let's look at some actual reactions. And stick around, because right after, we're going to have a quick-fire bonus round to see how they stack up against some other key players on the periodic table.
Okay, here's that classic reaction I was talking about. When you drop a piece of sodium metal into water, it goes crazy. It fizzes violently, producing hydrogen gas and sodium hydroxide. Now that sodium hydroxide is a strong base, which is also known as an alkali. And, ding ding ding, that's where the whole group gets its name, the alkali metals. And it's not just for show. This stuff is used to make everything from soap to paper.
Okay, now for the halogens. Let's set up a little competition. What happens when a more reactive halogen, like chlorine, comes face to face with a compound that has a less reactive halogen in it, like sodium bromide?
Well, the chlorine, being higher up in the group and way more reactive, just muscles its way in and kicks the bromine out. It's called a displacement reaction, and the coolest part is you can actually see it happen. The solution starts out colorless, but then it turns brown as the free bromine gets released.
And hey, here's a quick pro tip on naming. The word halogen literally means salt former. So it makes sense that when a halogen, like chlorine, gains an electron to form a salt, its name changes. The "ine" at the end gets swapped for an "ide", so chlorine becomes chloride, bromine becomes bromide, and so on. Easy peasy. All right, it is time for our bonus round. Let's talk about those transition metals. They make amazing catalysts. First question, for all the marbles. In the Haber process to make ammonia, what's the catalyst?
If you said iron, you are correct. Absolutely essential for making the fertilizers that help feed the world.
Okay, next up. To make margarine from vegetable oil, what's the catalyst?
And the answer is nickel. That's what helps turn liquid oils into solid fats. All right, last one. What's the key property that makes these guys such great catalysts? Something that really separates them from groups 1 and 17.
It is their variable oxidation states. That's a fancy way of saying they can have multiple different positive charges, which makes them super flexible in reactions, unlike the fixed +1 of group 1 or the -1 of group 17.
Okay, so we've seen how versatile other players on the board can be. But let's get back to our main event and really lock in the single most important thing to remember from this Group 1 versus Group 17 showdown.
Seriously, if you remember only one thing from all of this, make it this right here. The entire story, all their properties, all their reactions, it all comes down to one simple, powerful drive. Group 1 must lose one electron, and Group 17 must gain one electron. That's it.
Let's try an analogy. Imagine Group 1 is like a collector who has a perfect, complete set of something, but they've also got this one extra, awkward piece that just doesn't fit. It's driving them crazy. They are desperate to give it away just to feel complete. Now Group 17, they're the opposite. They're a collector who is just one piece short of finishing their set, and they will do anything to find that last piece and finally feel whole.
And here it is, your ultimate side-by-side summary. On the left, you've got the givers of Group 1. They lose one electron, they're soft and malleable, and they're excellent conductors. On the right, the takers of Group 17. They gain one electron, they're brittle and colorful, and they're poor conductors. It's a perfect contrast.
So, let me leave you with this final thought. When a giver, an element that is just desperate to give away an electron, finally meets a taker, one that's desperate to gain one, like when sodium meets chlorine to make table salt, they form one of the strongest bonds in all of chemistry, a perfect match. It really makes you think, doesn't it? What does that tell you about the incredible power of finally finding stability?